Hi, Brian Miller-Hicks again. So we are now going to discuss the engineering geologist's role in slope stability. The engineering geologist is a critical team member in assessing slope stability. Slope stability and slope instability, meaning landslides, slope failures of various kinds, are very widespread and very common throughout slope areas, hillside areas of the United States and around the world. Billions of dollars in damage are caused by mass instability, mass movement slope failures around the world. Many thousands of injuries and hundreds of deaths are caused by these phenomena if they are fast moving enough, or evacuation orders are not given, or some combination of factors lead to the loss of life and injury as well as property damage. So again, the engineering geologist has a vital role to play in assessing these failures, assessing slope failures as they occur, during their movement, after their movement, and provides some significant crucial data to design engineers to develop methods of mitigating slope failures. So reconstruction, removal of unstable material, and so forth. So we're going to cover some of that in a short fashion. This isn't going to be too long. I'm not going to get into too much engineering detail, as it were, but know, again, that the engineering geologist is a vital member of a team in assessing damage, in looking at these different kinds of slope failures and coming up with preventative or mitigation measures. So we want to be able to identify these features and to map where they are, to see where they are on the Earth's surface or in relation to a project, construction project, roadway, housing, what have you. So we want to do some mapping and planning. So again, this is not just for features, slope failures that have already occurred. We also extend our assessments to areas that are potentially unstable, may fail in the future, and we may be able to undertake some preventative measures before disaster strikes. So here's a section of a map from a USGS geologist, or excuse me, California Geological Survey geologist, Mr. Tan. He and others compiled these maps in 1995. So this shows in the La Jolla area of San Diego some basic configurations of suspected landslide areas. Suspected, that's why you see question marks here. And these numbers here have to do with the severity of potential slope movement. So the higher the number, the more vulnerable the slope areas are to actual landslide or slope failure. Over here with the solid black arrows, this is a well-defined, definitely known landslide that has been identified and mapped. So this is a definite slide. All the other areas are potential slide areas, but not definitively mapped and identified. So as you may imagine, these are pretty important planning tools, these maps are. If you want to build your house in here, you'd have to hire a geotechnical engineering firm and geologists to assess whether indeed your property is underlain by slide-prone geology, weak rock, slide plains, etc. Okay, so let's talk about the analysis and the engineering that goes into it. Slope stability is really a balance between driving forces and resisting forces. So what engineers and geologists try to do is define a particular slope's factor of safety. So the factor of safety is defined as the uh, resisting forces, uh, the resisting forces divided by the driving forces. R for resisting, D for driving. So if the driving forces are greater than the resisting forces, the slope is unstable and the factor of safety is less than 1, okay, according to this ratio. If the resisting factors are greater than the driving forces, then the slope is, by definition, stable with a factor of safety of greater than 1. Okay? So what are these driving forces and these resisting factors? Well, the driving forces include, of course, gravity. You can't have any downslope movement of material without the driving force of gravity pulling stuff down. Slope steepness, obviously on a very steep slope, you get faster movement of material, but a steep slope isn't necessarily stable, isn't necessarily unstable just because it's steep. A steep slope may mean the ground is underlain by a hard, resistant bedrock which can stand at steep angles. Sometimes very gentle slopes are the weaker slopes because the reason they are gentle slopes is because they're underlain by weak, unstable materials like sheared soils or soft soils. Okay, so keep that in mind. Slope steepness doesn't necessarily mean the steeper you are, the more unstable you are. And of course, moisture or water is a huge factor. You add water to the mix, you add water to soil that's already weak, it can begin to separate grains of soil or even grains of bedrock and cause volume changes and weakens the soil or rock mass. So water is a very important factor. And of course, during periods of high storm events, heavy rains, etc., that's when you see a lot of slope instability and slope movement, including fast-moving debris flows or avalanches. As I've already mentioned, weak, fractured, or sheared material means it's inherently weak stuff, so it's going to mobilize and move, especially if water is added to it. Well-defined failure surfaces. Let's say you have a hillside that's underlain by bedded sedimentary rock, layered sedimentary rock. If that sedimentary rock is tilted downwards and out of a slope, that may mean a weak plane develops on, let's say, a clay stone on that inclined bedding, and the stuff above it may slide on that clay stone downwards, okay, on a weak incline, sheared, weak material like clay. So that would constitute a well-defined failure surface. Overloading, of course, the more weight you add to a slope mass, the more prone it is to movement. Let's say you have a weak material near the top of the hill and you go dump a bunch of gravel or fill on top of that. Well, that might not be a good idea to do that because it could overload the slope and it may fail. Earthquakes, of course, can be monumental driving forces behind the occurrence of slope movement. You get that strong ground shaking, shaking up not only weak materials, but weak saturated materials, or even bedrock. It can fracture and cause bedrock to come apart and add to the instability of particular slopes. So earthquakes are sometimes a huge driving factor. Fire and deforestation are secondary factors. Secondary because they can contribute to the killing of shrubbery, vegetation, and trees, and the root systems of those trees and vegetation may help hold the surface layers of soil together so it doesn't slide down the hill. So if that's gone, you lose that strengthening factor and you open up more vulnerability for superficial material to slide down slope. Okay, so let me back up. Well, let me just talk about resisting forces. Resisting forces include friction. They include the strength added by tree roots and vegetation. The strength of a material adds to resisting forces. And what else? Natural buttresses at the bottom of a slope, like let's say you have a slope that ends buried, the bottom ends buried beneath a river channel. River channel is flat, so it actually may help buttress that material at the bottom or near the bottom of the slope. Okay. So here's one way we analyze a slope and determine its factor of safety. I'm not going to go into a lot of detail with the equations, but this kind of analysis is used by engineers and geologists to determine factors of safety. So it's called the ordinary method of slices. The most common method of slices used by engineers and geologists is the Bishop's method of slices. So what you do essentially is take your slope as it exists and slice it up into vertical slices, like so. And then you take each individual slice and analyze the forces acting on it. So you have weight or gravity acting on the slice, pulling it downward. You have the normal resisting force, which consists of some of the strength factors of the soil and the soil strength and friction. The friction component is actually acting parallel to the bottom of the slope or the failure surface. And here also, pore water pressure interacts with soil material. If you have high pore water pressure or high saturation, that reduces this effective end force, makes it weaker, so you have more ability of the material to move. Okay, so slice by slice, you take the weight of each slice, gravitational component, frictional component, normal component, and you kind of toss all that data into a set of equations, and you come up with a factor of safety, either greater than 1 or less than 1. And you can do this with a number of different configurations for shape of the failure surface, assumed failure surface, or different configurations for this center of the arc that you're going to draw, cutting through the slope as shown here. Okay. So how do we mitigate some of these situations? Well, here's a simple graphic that shows some of the ways you can do that. So let's look at this slope up here. This material is slid and failed into this valley. So what you want to do to stop any further movement is maybe you put a culvert down here for drainage of water, and then you fill this ravine with engineered densified compacted fill that holds this entire mass back so it can't slide anymore. Simple solution, not applicable everywhere. And the major part of the landslide is left in place, so that may not be desirable for all scenarios. Over here we have a mass that is sliding or has slid. So in this case, we take all this unstable material out, and we make sure we get down to the slide plane at the bottom. The slide plane typically may be a weak, sheer, gooey clay, not always, but sometimes. And you take that out, make sure you get down below the slide plane with your excavation. Then you put in a recompacted, essentially you reconstruct the slope with engineered compacted densified fill. So you take it down, so this dotted line is where this failure surface was, this dotted line here. Take all that out, and you go below it, and then you put in a wedge or a series of wedges of compacted fill, reconstruct the slope, and stabilize the slope. Hopefully that fan's not interfering too much with the sound. Um, so let's talk about a local example of a landslide which caused property damage to a roadway and to a number of homes. Fortunately, did not cause any deaths or injuries. So this is the Soledad Mountain Road slide, happened on October 3rd, 2007. This mass slid for about 45 minutes in a easterly direction, about 25 feet or so. The depth of the slide mass was around 60 feet, and this particular slide was a reactivated portion of a more ancient, older, larger slide mass. Okay, so this took out this part of the road and continued onto this road here. It destroyed 4 homes, damaged 3 others, and took out the roadway. Of course, destroyed and damaged many utilities as well. So here's an aerial photo of that slide, and the direction of movement is toward the bottom of the picture, as shown by the blue arrow. All right, so how was this repaired? Well, like I already mentioned, we took out the unstable mass, was taken out down below the slide plane, and then these structures were put in place. You see here, you see here. This is a row of what we call caissons, which were drilled in place through the slide debris. The material within these boreholes was removed, and then steel cages were put into these boreholes, and then concrete poured in afterwards. So the intent of this is to actually pin the hillside so it doesn't move anymore. So that's why these are called shear pins type caissons. So here's a row of pins here, here's a row of pins here. Each pin was 42 to 48 inches in diameter and went something like 60 to 66 feet deep. Well, after these pins were driven into place, put into place, then the slide mass could be excavated out. All the unstable material was removed. So here's the upper part of the slide with the shear pins in place, slide mass removed, and this entire slope was re-excavated, reconstructed with compacted fill, as shown here in the completed road and slope repair. So from beginning to end, it took about a year to repair this fairly massive slide. Okay. Now, more recently, this disaster occurred. This is in the town of Blatten, Switzerland, before and after the massive glacier slope failure in May 2025. Here's the nice, beautiful village of Blatten before, and here it was afterwards, roughly. This glaciers on the side of the mountain started melting, mixing with shattered rock and soil, and swept rapidly down slope. Now, fortunately, geologists were there, and they were able to see the signs of what was happening, and were able to warn people in the town. And so the entire town was evacuated, which means the prevention of injury and death. I think there was actually 1 known fatality. So what do you do in this case? Well, this is a huge event with probably millions of cubic yards of material moving down slope and causing damage and destruction, as you see here. Post-evacuation, buried and flooded the town. What do you do? Well, sometimes the best thing is to just get out of there before something happens. They couldn't really stop the melting of the glaciers. They couldn't really stop the water infiltrating the soil and rock. They couldn't stop the actual slope failure, so they told everybody to get out of town, and that prevented much injury and much death. So thank you for watching, and we'll see you for the next presentation.